started with cross-coupled, then we did a clocking, we made it SR latch or SR clock latch, then we made a D latch out of that. We didn't like the transparency, we made it transparent, but it was a D. Then we went back to a SR non-transparent, which became JK. Then we played around with it, made it a T flip-flop, and then we said T flip-flop is good because it has the property of doing something like a frequency divider. That's fine. We'll get back to that later. We also talked about the D flip-flop, and D flip-flop is easy to analyze, and every flip-flop can be made out of a D flip-flop. Okay, so if you decide later on you want a JK and you only have a D, you can always turn it into a JK. Actually, any flip-flop can turn into another flip-flop with proper logic. What I want to do now is, so far, what we've been saying is after the edge of the, I didn't intend this heavy color, but this is it. After clock goes from 1 to 0, okay, that's when the output is affected, when the Q output is affected. Okay, what it really is that when the clock goes like this, on this half, the input is collected, sits between the two latches. Remember the timing. And then after that, when the clock goes back to 0, this timing, the middle point gets propagated to the output of the second latch, which becomes the output of the flip-flop, and that's when you see the output. That's the clock. If you don't look at this details and you don't look inside the flip-flop, it appears as the output is affected after the falling edge of the clock. Okay? It appears as such. But see, the truth is, it's really not that. This is a level that requires at one time the clock to be 1 so that the input goes halfway, and then clock to be 0 so it goes the other half. If we say it's an edge trigger, it doesn't really mean it's an edge trigger. Okay, after the edge, the output is affected. That's true. Okay, but this edge is not the only thing that does the complete job. A duration of blue, clock is 1. Duration of red, clock is 0. These collectively take the input and put it on the output. Okay, fine. What's wrong with that? What is wrong with that is timing. My structure requires this much of time at least for the input to go halfway, this much of time for the input to go forward to the output. Okay? Which means that the clock duration has to be at least equal to the blue area. The next clock cannot be too close to violate the red area of the present clock. Okay? What it means is the operation of my circuit will be limited by these two red and blue areas. Okay? The blue area limits the duration of the clock. The red area limits how close the next clock is to this clock. There is a solution, okay? There is a solution, and that is designing an edge trigger D flip-flop. An edge trigger D flip-flop means I don't have the blue area, I don't have the red area. Instead, what I have is an edge, either a falling edge or a rising edge. Collecting the input happens on the beginning part of the rising edge. It appearing on the output happens on the second part of the rising edge, or falling edge, or if we are talking about falling edge, this is when the output is affected, and this is when the input is collected, or is observed, or is collected into some structure of the flip-flop. And therefore, edge trigger flip-flops are faster than master-slave. Okay? Let's do a flip-flop that I claim is an edge trigger, and let me prove to you that it is an edge trigger. I start with this, and I start with a 0 on the clock, a 0 on data. I start with my clock being 0, my data 0. Okay? Everything is peaceful, nothing is happening. At one point, I change my data from 0 to 1. I keep my clock 0. This becomes 1. This becomes 0. Okay? Let me go back to the black color and propagate the black color in the throughout the circuit. So there's a 0 here, 0 here. Since there is a 0 here, there is a 1 here. Remember that when you have a NAND gate, an input of 0 gives you an output of 1. No questions asked. Okay, you don't really care about the other inputs. The 0 causes this to be 1, and the 1 I have here, the 1 I have on the lower input of it, that's 2 1s here, and then the output becomes 0. There's a 0 that supports a 1 there, and let's assume that this is 0, and Q is 0, and therefore this is 1, and so I have all the node values, and everything is nice and quiet and peaceful and stable. Okay? Notice that I do have a cross-couple. But then this cross-coupled is a NAND cross-coupled. Unlike the NOR cross-coupled, that 1-1 is the illegal situation, the invalid. For the NAND cross-coupled, 0-0 is invalid. And 1-1 means hold your state. Hold your state. Don't change it. All right, remember, 1-1 for the output cross-coupled means don't change it. I change my data from 0 to 1, and let's propagate that change. There is a 1 here, there is a 1 there, 2 1s that become a 0. A 0 here, that means there is a 1 on this lower input, and then let's see what else is changing. There is a 0 here. Okay. A 0 here means a, let me make sure there is a 0 there. Yes, there is a 0 there. And therefore there is a 1 here. There is a 1 here. There is a 0 here. There is a 1 here. And that's it. I have 2 1s on the cross-coupled, and therefore no change. 0, 1. Okay. What has happened was my Q, okay, which started with 0, after the clock becomes 1, my Q remains 0. I'm sorry, after data becomes 1, it remains 0. I'm going to change now my clock from 0 to 1. I keep this a 1, and I want to find out what happens to Q. Clock changes from 0 to 1. This remains at 1. Okay, now the one that changes, that's the one you propagate. Clock changes from 0 to 1. I have 2 ones on this NAND gate, that gives me a 0. A 0 comes here, that gives me a 1. Okay, the data is a 1 and another 1 there, that gives me a 0. Okay, and so let me erase these the clock and data. I'm putting them on the side so there is room for more values to put in there. So there's a 0 here, and therefore now the brown 0. There is a 0 here, there's a brown 1 on this, there is a 1 on the upper input, the clock is 1, so there is a brown 0. This is stable. Look at the output now. The output has a 0 on the upper NAND gate, so this is a 1. I have 2 ones on the inputs of the lower one, and therefore this is 0. So what happened was, after clock goes from 0 to 1, my Q becomes 1. Okay, I'm going to change my data to 0. Okay, I'm going to change my data to 0. Remember, in the case of JK, when the clock becomes 1, it takes the data. When the clock becomes 0, then it still affects the output, but then that happens after the output. The D value during the clock will propagate to the output. But then let's examine that similar situation here. All right, so what do I do now? I set my D to 0. Okay, that's during the clock. In case of master say that was dangerous. I set my D to 0. I keep my clock to 1. Let's propagate that D0 to the circuit. See, I have a 0 here. That means that I have a 1 here, a 1 here on this input, and the clock is 1. The input is 0, so this is a 1. Okay, a 1, and the clock is 1, so this is a 1. The upper input is a 1, and therefore this is a 0, and there is a 0. I have to propagate all these values until I'm sure that everything is stable. Okay, so the green 0 is here. I have a brown 1 on top, and therefore this is a 1 here. Stable, stable, stable. Everything is green. Now let's look at the output. The output, the 2 inputs of it, 0, 1, hasn't changed, and therefore this remains a 1. This remains a 0, and therefore this remains a 1. Q remains a 1. Okay? What I'm going to do now is change the clock back to 0. Oops. Change the clock back to 0. Okay. Clock changes to 0. This is still 0. Clock changes to 0, so I propagate that since this is a 0, this is a 0, this is a 1, the 0 on the lower input makes this a 1, okay? The 0 is a 1 here, and this 1 is stable because of the 0 on the clock. I have a 1 on this input. I have a 1 coming from the input, this one here. Okay, and therefore the output is 0. There's a 0 here, there is a 1 here, so that's a stable. I have all of these values, and then notice I have 1, 1 on the cross-coupled on the output, and therefore I have a 1 here, and I have a 0 here. No change. What it means is my output, no change. What you're really saying is that the only time that my input, my D input, is observed, the only time that my D input value is taken seriously is when the clock is making a 0 to 1 transition. Okay? This is the only time that the value of D is taken seriously. The value of D at this point is 1, and therefore that 1 after the edge of the clock, after the rising edge of the clock, goes from 0 to 1. If I had changed my clock if during the clock I change my D to 0 to 1 to 0, nothing affects it. You are also seeing that the falling edge doesn't have an effect either. Okay? By this waveform, by this analysis, I'm showing that this structure is a rising edge D flip-flop. It is not transparent. What it means is that it has no choice. It has no chance of being transparent because only on the edge what is happening is happening. Only on the edge you are going from you're taking the input and taking it all the way to the output. So it can't be transparent during that edge. I refer to this as rising edge D flip-flop, and this is the notation for it. Rising, CLK, C1, 1D. Okay? And even though for the previous flip-flop, I showed you a symbol, at one point I showed you a symbol like this, okay? To kind of imply falling edge, that was not a true falling edge. A true falling edge is one if, for example, the clock is inverted, that would be a true falling edge. All right, so this is my flip-flop. Something that I haven't done so far is whatever flip-flop I showed you, I have assumed, any analysis I did, I assumed the output is 0 or the output is 1. Okay, and so if you ask me how does the output become 1 or it become 0, I say, well, let's clock it and then put a 0, and then our analysis goes on from there. Okay, what if I want to have a different way of kind of forcing the output to 1 or to a 0? Okay, let's take this flip-flop as is. Let's take this flip-flop as is and add a mechanism for setting it to 0 or setting it to 1. So I'm starting with this flip-flop, which is a D flip-flop, rising edge, and a Q. Let's not worry about Q bar. In order to force the output to 0, I can always put a signal into the lower input and set that to 0, and the output becomes a 1, and the Q bar output becomes a 1, and therefore Q becomes a 0. So let's do this. Let's say that if I bring in a signal from here and put a 0 into this, putting a 0 into this causes a 1 here. A 1 here will cause a 0 here, so my output becomes 0. So I say, well, this is an active low clear input. That means clears the output, clears it to 0. But see, the problem with this is if I change the value of 0 on this line back to 1, then the flip-flop goes back to its value. I don't want that. What I want is I want a signal that is asynchronously or independently comes in and sets my output to whatever value, in this case 0. In order to do this, I'm going to bring this input without explaining the logic behind it. I'm bringing this input to this lower gate NAND gate, as well as this, like I said, without going through the logic of it. And then this becomes my active low clear input, or active low reset input. What it is I have created an active low reset. Notice that this active low doesn't require the clock. What it means is it comes in and forces the output regardless of what value of the clock is. It forces it all the way to the output, and when it's gone, that means when it becomes active, it forces it to 0. When it's back to 1, then the 0 remains there. And therefore, I call this an active low asynchronous reset. Asynchronous meaning that it doesn't have anything to do with the clock. Okay, it's independent from the clock. Why not add an asynchronous preset? Look, the same argument I said. I bring in a signal, and if I put this into this gate, anytime this becomes 0, the output becomes 1, and the output becoming 1, the complement of it becomes 0. Okay? But then that's not enough. What I also have to do is, in order to make sure that after the signal I'm talking about becomes 0, back to 1, I don't want the output to go back to 0 again. I want the output to retain its 1 value. I call this one preset. Or set input. Okay, and then I also bring this to the gate behind it, so that when it goes back to 1, the effect of it remains. This becomes an active low. This was S. That was R. This one is S. This is a rising edge D flip-flop with active low reset input and active low set input. Like I said, this is referred to as preset, and often they put a bar on it, meaning it's active low reset, active low preset. This is referred to as clear, and then again a bar on it means active low clear. These are referred to as flip-flop control. Okay. Let's do something. Let's do a flip-flop, Verilog description for a rising edge D flip-flop with an active low reset input. Okay? I don't want the preset or the set input. I just want to implement this in Verilog. Module D module DFF asynchronous reset input clock reset output reg Q. Okay, always on the pulse edge of the clock. That's one way to come into the procedural block always. But see, I said that my active low reset doesn't need the clock. It can come in, and when it becomes 0, it can come in and set the output to 0. And therefore, negate when it becomes 0, reset, if reset, or ST I'm calling it, or ST, okay, tilde or ST, that means if it's 0, Q gets 1, tick B 0, else Q gets D. Oh, D in, D in. So this is this, which is this. Which is this. Which is the diagram on the left without the brown lines. And if you don't have the active low reset, all there is to it is when you come in there, you say always. See, if you don't, the original flip-flop without any set and reset, it is always pause, edge, clock, Q. Q gets D in. Okay? So when the positive edge of the clock arrives, you come into this, put Q, put D in into Q, and that's all there is to it. All right, this is an edge trigger flip-flop without going through the analysis that I did before. This is a master-slave D flip-flop, and this is also a rising edge master-slave flip-flop. Once again, a lot of times, even though this is not true edge trigger, but the symbol, because this is a very nice symbol, the symbol they use is the same as edge trigger. But when they say master slave, it means that it's not edge trigger. Let's analyze this circuit. So let's start with C0, D0, and let's assume Q0, C0. So there's a 1 here, There's a 0 here. There is a 1 here. There is a 1 here. We assume this is 0. This is 1, stable. And we are saying D is 0. And therefore there is a 1 here. See, the NAND gate, as soon as one input is 0, you know the output is 1. And you have a 1 there, you have a 1 here, you have a 0 here, so you have a 1 here. And the output is 0, so the master is 0, and therefore this is stable. And D is 0. Then what I'm going to do is I'm going to change D from 0 to 1. Okay, I change D from 0 to 1. Clock stays 0, so this is 1, this is 0. D changes to 1. D changes to 1. I have two 1s here, this becomes 0. I have a 0 here, this becomes 1. I have a 0 on the top, so this becomes 1. And I have a 1 on the lower NAND, the 1 there. I have a 0 here. And so what I have is a 1 on top. See, a 1 here, a 0 here. Okay, but then my clock is 0. Since my clock is 0, there is a 0 here. There is a 0, or the clock bar, or this thing over here is 0. And therefore the blue one only reaches this far. Okay, from this point on, I still have a 1 here. This hasn't changed. This hasn't changed. These don't change, and therefore this is still a 0. This is still a 1. Okay, so D changed. It came in this far. Okay, until D remains the same. Clock becomes 1. Okay, clock becomes 1. This becomes 0. This becomes 1. Let's see what happens on the left hand side. Now, something I also have to say, that you notice that when D changes and comes in the middle, in the master, Q stays the same. What happens at this point, we don't know yet. And so here we are. C is 1 now. D continues to be 1. And I have a 1 here, I have a 0 here, I have a 1 here, a 1 here, a 0 here, I have a 1 here. Now, the two ones, the two red ones, keep the cross-coupled NAND outputs the same. Okay, that means even though clock became made the transition from 0 to 1, these two remain the same. The master remains the same. Nothing happens. Actually, what happens is from this point on. From this point on, my clock is 1. Look at the red one. Now, see, this clock is 1. This clock is 1, and therefore the two inputs are no longer 0, 0 to hold a 1, 1 here. A 1, 1 means the Q output doesn't change. Now, since this becomes 1, this becomes 1, now you're seeing the effect of that big red one on the master. The effect of that goes into this. This 0 goes into this. I have 0, 1, and therefore the 0 here causes this to become 1. The 1 here and the 1 here causes this to become 0. And therefore my master started working here. And it reached the value 1 from the D input into the output of master. Stayed there until clock became 1. So even though we are saying this is a rising edge flip-flop, but then the timing between the D and the rising edge must be a longer time than the edge trigger flip-flop. And therefore, this is called the master slave. The notation is this. This timing that I'm showing between when D becomes 1 and clock becomes 1 is the timing that the master propagation. This is master propagation. Actually, into master propagation, meaning from this to this. All right, this is done. And then we go to the next work.